हाँ। अरे बट मुझे रंजीत सर बोल के गए टाइमर खत्म हुआ तब स्टार्ट कर देना। बहुत मुश्किल है ठीक है। Hello everyone, I am Manya Gupta, the Business Development Engineer at Paanduv Applications, sitting here in Bareilly, Uttar Pradesh on this beautiful sunny day. Welcomes you all to our webinar Developments in AM PravaH for Authentic Additive Manufacturing Simulation Experience. I am so thrilled to be here today to discuss about all the latest developments that are done by the R&D team of Paanduv Applications to enhance the simulation accuracy and user experience. But let me first ask you this question that we all are so tired of the traditional manufacturing limitations, aren't we? So, I mean, additive manufacturing has a lot of significance in other industries also, whether it is healthcare, aerospace, consumer goods. So, and I would like to tell all the ladies out there also that additive manufacturing is marking its sprint to the fashion industry also. So, let me know in the comment section that what are the other industries you want AM or you know that AM has the significance on. So, in this webinar, we are going to cover the capabilities that AM PravaH has had so far and all the current and latest developments that we have made in the upcoming future versions of AM PravaH. And we are also going to have a live Q&A, so you can all just type your queries in the chat section below. So additive manufacturing has been done using a lot of processes such as LPBF, DED. Um, I would like to have a question from the audience that what is your favorite additive manufacturing process and what part do you particularly fancy about that process? So let's start with a quick recap, shall we? So you might have been familiar with the version 1.5 of AM PravaH, the world's first all-inclusive 3D computational software for additive manufacturing. It comes with three modules that are microscale modeling, microstructure modeling, and artificial intelligence, in which the macroscale module consists of particle dynamics, laser dynamics, thermal fluid modeling, including the four-phase multi-phase dynamics, Marangoni convection, Fresnel reflection, and keyhole formation. The microstructure module includes the microstructure analysis, grain size analysis, Euler angles, grain misorientation. And the artificial intelligence uses it utilizes the simulated and experimental data for better process parameter optimization for better decision making. So this is one of the part that we cover in the macro scale modeling of AM PravaH. This satisfying video simulates the DEM of Ti-64 powder spreading over the metal substrate. As you can see, the difference in colors symbolizes the variation in the radius of the particles. It's satisfying, isn't it? And check out this video of simulation of melt-cool dynamics, which consists of four-phase multi-phase system, Marangoni convection, and Fresnel reflection. So beautiful, right? I think I have to relate with Captain America on this, that I can watch this all day. So these are the two simulation visuals for keyhole formation due to Marangoni convection and Fresnel reflection. This is the stable white keyhole, and this is the dynamic keyhole collapse. Look how effortlessly this simulation is running. Let me know in the comments if you relate with me too. You can also customize your LPBF scan pattern of laser. For example, this is a zigzag pattern. You can also choose circular or any kind of you like. This is a simulation for grain evolution in multi-track LPBF process using AM PravaH. It comes under the microstructure module and it is based on the Monte Carlo pot algorithm. And this simulation is for the material Ti 64 laser power 280 watts. So these are some of the defects that you can predict using AM PravaH, such as keyhole, lack of fusion, balling, porosity, and there are many more. So this is just not all with AM PravaH and its older versions. You can also discover you can also know about all the capabilities that the older versions of AM PravaH had. And for that, you can refer to the previous webinars. My team will be posting a link in the chat section. You can click on it and get to know all the capabilities that all the previous versions of AM PravaH have had. So I would like to request to our audience that buckle up because we are going to delve into the developments that we have made in the upcoming and the latest version of AM PravaH for authentic additive manufacturing simulation experience. So who are we? We are Paanduv Applications based in Bareilly, Uttar Pradesh. Paanduv Applications was founded by Mr. Advait Gupta. He is an MS from Stanford University, and he holds expertise in computational physics and artificial intelligence. He is also the lead developer of AM PravaH. We are a cutting edge technology company that provides scientific software development services integrated with computational physics and artificial intelligence, with a highly interdisciplinary team of researchers and engineers. So I would like to welcome Mr. Prithvi Uttarwar. He is also a research engineer at Paanduv Applications, and he will be telling us of all the latest developments that we have done in the latest versions of AM PravaH. Over to you, sir.
Thank you, Anya, for the kind introduction. Let me share my slide. Yeah, is it visible? Yes. Yeah. So hello everyone. Hope you have been enjoying the webinar. So thanks Manya first of all for the kind introduction. So we will talk about all the developments we have been doing in AMPravaH and what we have achieved till now. So last year in November 2023, we launched AMPravaH 1.5, which has many distinguishable features such as four-phase system which include shielding gas and vapor. And then we have Marconi convection, we have nice visualization tools, we have terminate simulation features, we have a launch console to see the simulation progress. Then we have residual plots and we have a nice modern GUI. So after that, we in December 23, we released version 1.6, which was basically improvised version of version 1.5. So to make the user experience more robust and uninterrupted. So after that, we have been continuously developing AMPravaH to make it a more user-friendly, a more accurate, and more faster. So in version 1.7, we included microstructure analysis, scan pattern visualizer, power spreading visualizer, and a more realistic power spread. After that, in June 2024, we released version 1.8, which has many new features. It has a load project feature. It has feature to resume the simulation. Here we can create any new custom alloy. You can provide new shielding gas properties. You can give velocity to the shielding gas. You can create your own laser beam profile, and we have included modified time step calculation to make simulation more accurate and faster. So in current version 1.9, we have included temperature dependent material properties to make your simulation results more accurate. And we have included smart parallelization, and also we have included non-spherical particles and particle spreading with roller. So now we are currently at version 1.9, and maybe we will release this version maybe in next month or after that. Also, parallelly, we are working on version 2.0, which will be the major release by the end of this year. In this, we will include the complete new model, which will include the laser wire beading, same as LPBF. So let's see one by one how these all these features are empowering the AMPravaH to make it more accurate, more faster, and more user friendly. So now we see that AMPravaH is more accurate. So how we are making AMPravaH more accurate? So let's start from the powder spreading. So here in the image above, you can see that powder is being sprayed, dumped directly on the substrate. But this is not the case in real. So in the schematic below, you can see there is a powder reservoir and there is a spreader. Where using a recoater blade, we are spreading a powder over a substrate. So same kind we have implemented in our AMPravaH. So here you can see there is a powder dumped beside the substrate, and you can see the video. So now the spreader will spread the powder over the substrate to form a more realistic powder bed. So to get more realistic simulation results, we need to simulate the whole process as same as the as same it is in the real. So to get more realistic powder, we have included this more realistic powder spreading technique. So in this another video, you can see powder spreading for multi-layer. You can see that first layer has been already formed, and we are now spreading the powder for the next layer. So creating a more realistic powder bed will actually improve the accuracy of your simulation. Talking about the accuracy of the simulation, we know that in real particles are not spherical, right? They can be a little elongated or irregular shapes. So to include that, we have we have included non-spherical particles. Using this feature, you will be able to simulate different shapes of the particle. We call it superquatic powder particles. So it basically follows this equation to generate the shape of the particle. So using this feature, you will be entering the inputs A, B, C, N1 and N2, which are basically the excess of the particles, and the N1 and N2 basically decides the curvature of the particle. So using this feature, you will be able to mimic the realistic powder bed as you have in your real case scenario. So here is sim powder spreading simulation for the non-spherical powder. So you can see how this powder bed has been formed. So when we use a spherical powder, it is not that dense. But in real, since we have irregular shapes of the particles, the bed is more denser than what we get with the spherical powder. So using these non-spherical powder particles, we'll be getting more realistic powder bed, which is more denser than the spherical powder particles. Next comes the roller spreader. So along with the non-spherical powder particles, we have also included the powder spreading using the roller. So you know that when we use the roller, the powder bed is more denser and we get a better quality built part from our LPBA process. So in version 1.9, you will be able to use this roller spreader to spread your powder from the powder bed. Next comes the laser. So this is the melt pool simulation with non-spherical powder particles. So you can see how the bead has been formed after the solidification. So after the powder bed, next comes the laser. So earlier in version 1.5 we had only Gaussian laser beam, but in version 1.9 we have included customizable laser beam profile where you will be able to give your own customized laser profile. So here we have simulated three laser profiles. We have rectangular, circular, and a square laser profile. You can see how the mid pole is been formed with a different laser profile and what is the difference. So using these different laser beam profiles, you'll be able to mimic the parameters of your machine. What kind of laser profile your machine is being using. So same you will be able to simulate in the AMPravaH. Next comes the shielding gas. So we know that in chamber we use a shielding gas to keep the environment oxygen free and keep the environment clean, right? So moving shielding gas basically keeps the chamber clean. So we have included moving shielding gas. So user will be able to provide the velocity of the shielding gas and the flow angle. So in this video, you will be able to see that our gas is moving from left to right. So you can see the velocity vectors here and how the gas is moving and taking the vapor along with it. So shielding gas also has effect on the cooling rate of your bead, right? So when there is a moving shielding gas, the cooling rates will be higher. So it will basically affect your microstructure. So using this feature, you will be able to create more realistic temperature profile and more realistic cooling rates and hence more realistic microstructure. Next, we have temperature-dependent material properties. So we all know that thermophysical properties of any material, or maybe alloy, does not are not constant with the temperature. They basically change with the temperature, like density, specific thermal conductivity, and extension. So we have provided GUI to basically input the temperature-dependent material properties, and also we have made a modification to the solver. So now in with this built-in GUI, you will be able to give a number of points to basically uh, provide the curvature of your temperature dependent material properties. So using this feature, you will input your temperature and the respective values to basically fit the temperature dependent material properties. So we'll see the quick video of GUI how it works. So inside the material properties, we have solid alloy, molten alloy, vapor, and gas properties. So by clicking this button, the table will be open and you will be able to edit the properties inside the table. You will be able to add more points to the table if you want. Yes. And after saving these inputs, you will be able to run your Melpool simulation. So all these changes we saw were making the AMPravaH more accurate. So we'll see now what makes AMPravaH more faster. So we all know that for when it comes to numerical simulation, the Coron number is the most important parameter to generate the errorless simulation results and for the stable simulation. So here we have given a flexibility to choose your own Coron number. So it varies from basically 0.1 to maximum 0.95 in the GUI. So Coron number basically depends on velocity, delta t, and delta x. So to maintain that Coron number, what we have provided here, so earlier it was calculated based on the delta x and u value only. But now in the modified time step calculation, we calculate the time step depending on the temperature change, phase change, velocity, and Coulomb number. So before even there is any change in the velocity or a certain rise in the velocity, we detect any phase change and we detect that there will be a rise in velocity in the next step. So we modify the time step, we reduce the time step and keep our Coulomb number below what we have provided in the maximum Coulomb number limit. So this will basically keep your simulation stable and And when your simulation is stable, so it will basically reduce the complete simulation time, and you will get more accurate simulation results. So in this graphs, you can see how the modified, that is preventive approach, and the earlier reactive approach has different outcomes in terms of current number. So in first, you can see when there is a laser, when laser hits on the substrate or powder, there is sudden phase change due to melting, and the core number has reached beyond 5, right? But in the preventive approach, we don't see that core number has reached much higher. The maximum limit it has reached is 0.6. This is about 10 folds down reduction in the core number. So this will basically give you more accurate and hence more fast simulation, because your simulation will be now more stable. Let's now discuss what are the new developments which makes AMPravaH more user friendly, and we can do better analysis for simulation results using the AMPravaH. Let's see this 10 layer simulation. This simulation was a 10 layer thin wall simulation where yeah. So after first layer, there will be a powder spread for the second layer, and the simulation will go on. So you can see a nice core has been trapped here. So such large long simulation will usually take 1 or 2 days, and many times it happens that your power goes off or somehow your system turns off. So in earlier version there was no feature to restart the simulation. So user will have to restart the whole simulation from the beginning, and this can be frustrating for the user. So see how this stainless has been formed. So this simulation basically took about 28 hours. You can see we have captured the pore also. So make it more user friendly and reduce the repetitive simulation, we have included the resume feature. So we have buttons for terminate project, load project, and the resume simulation. So what happens when you run any simulation, when you basically save the inputs, it will actually save all the inputs in a single file. And when you hit the run solver, it will basically start the simulation, and along with it will continuously save the current simulation state of the simulation. So when you terminate the simulation, or your system turns off, you can load that previous project, and it will also load the inputs you have used in that simulation, and along with it will also input the current simulation state where it was terminated. So by using the resume button, you will be able to restart the simulation from the last point where it was terminated. So this will basically reduce the repetitive work of user. So then we have added a feature to create a new alloy. So let's say you have to work on any new alloy for getting optimized process parameter. So earlier there was no such feature to create a new alloy. You were able to just change the alloy properties in whatever default alloy was there. Now we have a feature to create a new alloy. By selecting this create new alloy, you will get a blank entries, and there you will be able to input your material properties, and then by using a save alloy, it will save the alloy properties in the default database. So when you are working with a new alloy, what you will do, you will save your new alloy, and then you will perform the simulation with some process parameter, and then you will analyze the melt pool defects and the microstructure. If you get the desired melt pool defects and the microstructure, you will use those optimized parameter to actually build the part in real. And if you don't get the desired melt pool and the microstructure, you will make changes to the process parameter, and then you will repeatedly you will feed it to the AMPravaH and perform the n number of iteration to get the optimized process parameter. So it will basically reduce the time to enter the material property each time you run the simulation. So similarly, you will be able to save shielding gas properties also. Then we have a nice feature to visualize our scan pattern. So this is our scan pattern. So we in the scan pattern we provide time, we provide x, y, z coordinates and a laser on off condition. So when we are creating a more complex scan pattern, we make we many times make mistakes, and we get to know that after running the simulation. Now we have added a nice feature. So by uploading the scan pattern, we can click on the visualize scan pattern, and then we can enter the number of frames we want to simulate to create animation. So this was a complex zigzag pattern, and you can see our visualizer scan pattern visualization tool is nicely telling animating how our scan pattern is in real. So using this cool feature, you will be able to create correct, accurate scan pattern before we actually go for the macro scale modeling simulation. Then in the visualization, we have implemented build region visualization, where you will be able to extract the build part of from your macro scale model, macro scale domain, and you will be analyze that build part. So similarly, we can visualize a solid part, the liquid part, the alpha gas, that is the shielding gas, the temperature profiles, the velocity profiles, the vapor, and the melted region. Witness this nice simulation video where we have shown the visualization of the built region. This was basically 5 layer overhang kind of simulation. So here you can see the scan pattern. So it is in steps. So we are basically trying to generate overhang part. So here you see the overhangs built in actual case. So when we are actually studying this kind of structures, we simulate this kind of patterns and try to see if the given offset parameter net spacing is enough or not. Then in post-processing part, we have thermal recycling plots, we have cooling rate plots, where you can put a small probe in your simulation domain and analyze the temperature variation time in that domain by plotting the thermal cycling plot and the cooling rates. So thermal cycling plots basically tells you after each layer how the bottom layer is being affected due to the laser moving for the next layer and subsequent upper layers. Similarly, we have cooling rate plots where you will be able to see the what is the cooling rate, that is how fast temperature is dropping when we give the cooling time for our bead, right? So basically cooling rates basically our microstructure formation depends on the cooling rate. So get a good microstructure, we need to study the cooling rate in our LPO process. Then there is a porosity evolution. Since we have added a build region extraction feature, we can now analyze the porosity for our build part. So earlier we used to cut the build section and analyze the density of it to basically calculate the porosity of a build part. But now since we have a separate build region extracted, we can analyze this build region, and we can compare the density to calculate the porosity after the solidification. Then in microstructure analysis part, we have different modules. Uh, we have included the whole tool for analyzing the microstructure. So there we have grain size distribution tool, and we have angular chord length distribution calculator. So using this, you will be able to get the idea of grain size and the grain length and the orientation of your grain, the microstructure. So after calculating these graphs, you will be able to gain an insight on the mechanical properties of your microstructure, such as strength, hardness, and the crack propagation. So this is the GUI of a microstructure analysis tool, right? So here you can see there is cut X, cut Y, and cut Z plane. So this is basically we are telling where we want to cut our microstructure and look inside it. So you will provide the value for the cut X, cut Y, and cut Z plane. So after that, you will just hit the calculate CLD button, and it will show you the cutted cross section of that microstructure provided plane, and also calculate the angular coordinate for that plane. Similarly, if you click on the thermal plane size, it will analyze the whole 3D microstructure and plot this probability distribution of your equivalent diameter for all your grains. So along with it, you get the mean of this distribution, standard deviation, skewness, and the kurtosis of this grain distribution. So we have a comparison study for angular coordinate distribution with a different shape of the melt pool. So we have a wide melt pool and we have a deep melt. So in wide melt pool, we can see the this coordinate distribution now, where we see the grains are oriented in all the direction basically. But in the deeper melt pool, we have grains mostly oriented in the horizontal direction. So this basically tells how our majority of our grains are oriented in which direction. So similarly, we have a study for the grain size distribution. So in wider melt pool, you can see there are grains with higher area or maybe higher equivalent diameter, right? So it goes up to 40, but in the deep melt pool, we have up to 16 or 18, right? So the average grain size in upper graph, we have 16 micron, and in the lower melt pool, we have average 8 micron of average grain size. So this basically tells how the majority of grain are, right? So these features basically make the work of user more easier, right? So now we will see a few interesting case studies we have performed. So this was basically a three-track simulation using the TI6 for alloy and laser power to 66 watt. So we were basically studying the height spacing in this case. You can see how the melt pool is been forming and how the solidification is been taking place. So after the complete solidification, you can see we have captured the defect. So here we have a lack of fusion defect, and also we have partially melted particles. So and you can clearly see that the given height spacing was not enough because the layer are not fused with each other to form a complete solid structure. Then we have a study for the microstructure. So this was a two-track, three-layer microstructure. So here we have a grain size distribution for this microstructure, and by using the average grain size, we have put it in the Hall-Patch equation to calculate the yield stress of this microstructure. So it comes out 989.17 megapascal into micrometer per square root of micrometer, right? So using this grain size distribution or your average grain size, you will be able to actually get the mechanical properties of your microstructure. Then we have a study for surface tension. So we told you that we have temperature dependent surface tension. So here we have study for high surface tension gradient, a low surface tension gradient, and the medium surface tension gradient, right? So this basically we are talking at the vaporization temperature. So in the case of high surface tension, where the surface tension is declining rapidly with the temperature, we can say there is a more spatter. And in this medium case, there is no much spatter, right? and in this low self extension gradient, there is very less spatter. So this basically shows how AMPravaH can capture the keyhole effect and the spattering effect due to surface tension, due to Fresnel reflection, and due to marangoni. So this was about up to version 1.9. Now we are also parallelly working on the version 2.0, where we have already made some improvements. So let's see what we have done. So this is a two-layer simulation for the laser wire DD, right? You can see how the wire is being melt and how the bead is being formed. So here there is a laser and continuously wire is being melted and the bead is being formed. So this basically will include a multi-track, multi-layer laser wire DD. It will be a complete a separate module as we have LPBF. So this was all from my side. If you want to more, if you want to know more about the AMPravaH, you can scan this QR code and submit your queries, or you can request for the free demo. Also, I request you to follow us on LinkedIn, on Instagram, and you can subscribe us on YouTube to get the daily dose of stunning simulation videos. So now we will discuss few questions from the we have received in our chat section. So we have a question: how user friendly is AMPravaH for beginner versus for advanced user? So when we ship the AMPravaH, we provide a full training for the AMPravaH. So the GUI basically is very user friendly, and within a day or two, the user will get to know all the features of the GUI. Will be able to seamlessly use the AMPravaH. So someone has asked if there is a student version available. So we don't have any free student version, but there is a teaching version we provide to the university. So you can basically request from scanning this QR code. You can basically request all that information. So someone has asked, is there NITI available? So in our current version, we don't have that alloy in our database, but we will try to include that. But also you can add your own alloy if you have the material properties available. So these were the questions. So as we have been continuously developing the AMPravaH, and we are continuously making progress. So there will be part two of this webinar we will be organizing. So you can right now register for the part two of this webinar using the link provided in the comment section. Right. So thank you all for joining us. So it was a wonderful webinar. I hope you all enjoyed it. So, yeah, thank you so much.